are given 0.1 normal solution of hydrocyanic acid, a weak acid solution, and were asked to calculate its pH. You don't have a pH meter or pH paper with you. What will you do? In fact, even if you have a pH meter, do you think that you can calculate the pH of a weak acid? In this context, I will introduce you a method to calculate the pH of a weak acid or a weak base. Consider the generic equation for the dissociation of a weak acid. In an aqueous solution, this weak acid will be partially ionized. Then, there exists an equilibrium between dissociated and undissociated molecules. The equilibrium constant for this can be written as Kc equals concentration of H3O plus into concentration of A minus divided by concentration of Ha into concentration of H2O. As the concentration of water does not change, you may write Kc into concentration of water equals concentration of H3O plus into concentration of A minus divided by concentration of Ha. Kc and concentration of water being constant, their product is also a constant and is termed as Ka, the dissociation constant or ionization constant of weak acids. The equation says if the concentration of H3O plus and A minus is greater, then larger will be the value of Ka, or in other words, the stronger the weak acid, the greater will be its dissociation. And the extent of dissociation or ionization of weak acids is represented in terms of degree of dissociation alpha. To understand this term, let us consider C moles per liter of a weak acid. If alpha is the extent of dissociation of this weak acid, then at equilibrium, the concentrations of reactant will be C into 1 minus alpha and that of products would be C alpha. Now, by substituting these concentrations in the equation for dissociation constant at equilibrium, you may write Ka equals C alpha square divided by 1 minus alpha. This equation helps us to calculate the dissociation constant if the degree of dissociation is known. You may also conclude that by knowing the ionization constant of an acid and its initial concentration, it is possible to calculate the equilibrium concentration of all the species. Usually, the value of Ka is very low. To accommodate such small values, logarithmic scales are usually used. You may express Ka as negative logarithm of Ka, which is termed as pKa. That is, the larger the value of Ka, the stronger will be the acid. Likewise, you may derive the equations for the ionization of weak bases. Consider the generic equation for the ionization of a weak base. Here, the ionization constant or dissociation constant of weak base BOH may be written as Kb equals the product of concentrations of OH minus and B plus divided by the concentration of BOH. If the initial concentration of the base were C moles per liter and its degree of dissociation alpha, then you may express Kb as the ratio of C alpha square divided by 1 minus alpha. As mentioned previously, similar to Ka, Kb is very small and is expressed in logarithmic scale as pKb. Thus, the pH scale for hydrogen ion concentration has been extended as pKb equals negative logarithm of Kb. Next, we may discuss the relation between the ionization constant of a weak acid and a weak base. For this, consider the example of ammonia and ammonium ions and the expressions for Ka and Kb respectively. Ka equals concentration of H3O plus into concentration of ammonia divided by concentration of ammonium ions. Similarly, Kb can be written as concentration of ammonium ions into concentration of OH minus divided by concentration of ammonia. Next, you may compute Ka into Kb. Solving, you will get the equation as Ka into Kb equals concentration of H3O plus into concentration of OH minus. This is same as Kw, the ionic product of water. You may also realize that Ka into Kb equals Kw from the molarity values of Ka and Kb. That is, Ka into Kb equals 5.6 into 10 raised to minus 10 into 1.8 into 10 raised to minus 5, which is equal to 1 into 10 raised to minus 14 molar. Thus, in the case of a conjugate acid-base pair, Ka into Kb equals Kw. This can be also extended to make a generalization. Here you can see the net equation obtained from equations 1 and 2, that is the equation 3. Equation 3 gives the auto-ionization of water and its equilibrium constant is Kw. You have seen previously that equilibrium constant for equations 1 and 2 are Ka and Kb respectively. This shows that equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constant for individual reactions. Hence, in general, you may write K net equals K1 into K2 into K3, etc. Besides, if we take the negative logarithm on both sides of the equation, then pK values of the conjugate acid and base are related to each other by the equation pKa plus pKb equals pKw. Now, from the above discussions, can you answer the question that I asked you at the beginning of the session? You were asked to determine the pH of 0.1 normal hydrocyanic acid solution. Let us try to solve this. From the current discussion, you might have noted the Ka value of HCN as 4.9 into 10 raised to minus 10. We may start by writing the equation for the dissociation of HCN in water. The initial concentration of the solution is given as 0.1 normal. Let alpha be the degree of dissociation of HCN. Then write down the initial concentration, change in concentration on proceeding to equilibrium, and the equilibrium concentration of all the species based on the generic equation that we have discussed. These values may be substituted in the equation for Ka. The acid being weak, the value of 1 minus alpha may be neglected. Rearranging and solving, you will get the value of alpha as 7 into 10 raised to minus 5. From the table, it is understood that the concentration of H3O plus is 0.1 alpha. Substituting the value of alpha, you will get the concentration of H3O plus as 7 into 10 raised to minus 6. Now, the pH of the solution may be calculated as pH equals negative logarithm of hydronium ion concentration, which is equal to minus log 7 into 10 raised to minus 6. Solving for this, you will get the pH of the solution as 5.15. So far, we were discussing the dissociation of monoprotic acids such as hydrochloric acid, hydrocyanic acid, etc. Here, there is only one ionizable proton per molecule. However, there are acids like oxalic acid, sulfuric acid, phosphoric acid, etc. with more than one ionizable proton per molecule. Such acids are known as polybasic or polyprotic acids. Can you write down the ionization constant for a polybasic acid? Do we have to write two Ka values here? Say Ka1 and Ka2? Well, we will discuss about this in a next video. Now we will summarize what we have learned.
Manorama Horizon. Learning made simple.